Like this is definitely a subject where there's a lot more stuff at the moment that's dreams than there is stuff that's like reality. So it's like very, like it's one of these places where it's like very exciting to like come and work because there's like a lot to do and a lot that isn't known. Yeah, and so I should kind of want this to be like an invitation for like you guys to join me and let's help figure it out. Okay, so there's a lot of different places that like one can start when studying 3D symmetry. It's related to like a lot of different things. The easiest way for like me to talk about it is to tell you like where I was when I first encountered it. And I was originally a geometric representation theorist, and like I was like mostly interested in the representation theory of like what I would call like an almost commutative algebra. And so like an almost commutative algebra is like one that's like closely, well, that arises as a deformation of a Poisson algebra. Like a more concrete way of saying that is that a graded deformation quantization of weight n is a graded algebra over the polynomial ring in H bar, such that so it's a graded algebra, so one needs to say what is the weight of H bar, and so that's n in this case. It needs to be flat as a module over the polynomial ring. That's just so that when you, that it behaves nicely when you deform. And then the almost commutative part of this is that when you set H to 0, you get something commutative. And whenever you do this, you always get a Poisson bracket on the commutative ring that arises as the zero fiber of this deformation. And this Poisson bracket is defined in the following way. If you have two elements and you want to take their bracket, you just lift them both into your deformation, like you just lift those classes to compute just the ordinary like associative Lie bracket, AB minus BA of the lifts. And then now, because everything was commutative when you specialize H to 0, this thing will be like divisible by H bar. So just divide by H bar, that's okay since you're flat, and then just take the class mod H again. And this Poisson bracket will be like some operation which is of degree minus n. So it's going to just lower the degree by minus n. And whenever I have this sort of a situation, I'll say that the algebra A, which is like the fiber over 1, quantizes the commutative algebra that you get by setting H to 0. And for this, like I'm usually going to be interested in the case when H is, or say when n is greater than 0, and usually it's going to be 2.
Usually, 2.
So in the 3D story that I'm going to do, it's going to be an equivariant parameter for a C star, and those always have weight 2.
C star acts on symplectic form.
I mean, so that will also be a different reason that it's, but you could have made it be like 1 or other things, but this is going to be the reason that it's going to be 2 for me, is this reason about the equivariant cohomology secretly. Okay, so let me just tell you my favorite example. So my favorite example is a semi-simple Lie algebra. And like in that case, if you have a semi-simple Lie algebra, the universal enveloping algebra quantizes just the symmetric algebra. Like on this Lie algebra, this is just the PBW theorem. And the induced Poisson structure that you get is the constant Kirillov-Sarayu Poisson structure, where like the coadjoint orbits are like your symplectic leaves. But that's actually not going to be quite the kind of algebra that I like to study. The reason that I don't like to study this one is that it has a really big center. So by like the Harsh-Chandra like isomorphism, like the center is like W invariance functions on the Lie algebra of the torus. That means you're going to have like continuous families of like simple modules and things like that. And I would rather just have a ring that has finitely many simples. And so one way that you can do that is, it's like well known that like if you have like any simple module over a ring, then the endomorphisms are just like isomorphic to like scalars. And so that means that like if I have any, if I have like the action of the center that commutes with all of A, so that means for each center I'm going to get like a scalar. So if I pick out any simple, I'm just going to get some sort of a map from the center of my universal enveloping algebra, or if any algebra, into C, and once I pick out like such a map like this, I can just specialize my ring. They call it taking a central quotient, where I just take the kernel of this homomorphism coming from S. So I just get like some ideal, like here's the kernel. That thing will be a central ideal, so I can just mod out by this and get like another algebra. And so this thing I would call like the specialization compatible with S. And when I do this with the universal enveloping algebra, so I just pick some dominant weight that gives me some simple, and I can play this game. Then like I no longer quantize like the entire Lie algebra. I'm just going to quantize like one symplectic leaf, like of the Lie algebra, and the one that I'm going to quantize, it turns out, is going to be just the nilpotent cone. And so the nilpotent cone is just the space of let me just pretend for a minute that my Lie algebra is just like SLN. Then this would just be the space of matrices where like the characteristic polynomial, all the coefficients of the characteristic polynomial vanish. So you take all of those guys, and it's going to be like some crazy cone. And it's like well known, this is like a very famous object in algebraic geometry, and it's well known that this thing is resolved by the Springer resolution. So in the case when you just have G being SL2, well then your matrices that you're looking at are just the traceless ones, just ones in the Lie algebra. So they're like A, B, since they're traceless, the diagonal entries have to be opposite to one another. And then you've really only got one coefficient in your characteristic polynomial, which is just the determinant. And so when you work that out, you just find like this cone, this equation for a quadratic cone. And it's something singular where I've drawn like the real part looking like this. And this thing has like a natural resolution by T star P1, which is the cotangent bundle to the flag variety in this case. And roughly it just collapses like the central P1 down to a point. So it's just like this picture that you see here. And this resolution is like pretty nice. This cone like has like a natural C star action coming from the fact that it arised as like the central fiber in one of these quantizations. So it has a C star, so functions on it have this grading, so it has a C star action, and then this resolution is just compatible with the C star action. And like the C star action on T star P1 is just the one that scales the cotangent fibers. So this is like the kind of like thing that I was interested in.
So does the nilpotent cone depend on the representation you choose?
It doesn't. They all give the same, you mean the lambda?
Yeah.
No, it doesn't depend on the lambda. They all give you the same one. That's a good question. Okay, and then there's like a big story like due to Braden, Licata, Proudfoot, and Webster that shows that like many of like the good aspects of the representation theory of just the central quotient of the universal enveloping algebra, that they generalize to anything that they call a quantized canonical symplectic resolution. And like the main example is this resolution of the nilpotent cone that we just talked about. So just to revamp, or just to, I have my central Poisson algebra, and I can take its spectrum to get like a space. And I'm going to make the following geometric assumption on that space. So it has a C star action coming from the grading, and I want that thing to have a single isolated fixed point. And like what that means is just that the degree 0 piece, or the weight 0 piece, is just one dimensional. It's just a copy of C. And that'll mean that you've only got one fixed point. And then the other thing that I'd like to ask is that like the grading be like entirely non-negative. And like basically what that means geometrically is that like every single point has a limit under the action as you send, like if you act by sending Z to 0, and you act on any element, then like this will actually exist. And more generally, it'll actually be this unique fixed point. So like this, so the thing I have is that this cone, so the picture that you should have in mind is this cone has a dilation action that like that shrinks everything down to the fixed point. And then what I can ask for is like a resolution of singularities of this like Poisson, of this spectrum of this Poisson algebra. And I say that that resolution's conical if the resolved guy has a C star action, which is compatible. And then I say that it's symplectic if the Poisson structure on the smooth part of this cone, well, one, that it's non-degenerate, so that means that it defines a symplectic form. So let me remind you like what that means. So like a Poisson bracket is equivalent to the data of like a bivector. And in particular, it like gives you a map from the cotangent bundle to the tangent bundle. And it's non-degenerate if this is an isomorphism. And whenever that's true, then your Poisson bracket actually also defines for you a symplectic form. So what I want is that this Poisson bracket, which is coming from my non-commutative algebra A that's quantizing this Poisson guy, I want that to be a symplectic form when you restrict to the smooth locus. And then you can take that up to the resolution. You can lift that symplectic form up, and I want it to actually extend over the whole space. So like basically like, right, the smooth locus will pull up to just part of the resolution, and like I want it to have like a holomorphic extension. And so that's like actually like a pretty strong condition. And like
The complex surface, the resolution?
so it can be a complex variety of any dimension.
Oh, man.
Yeah. So I just have some Poisson cone.
For SL2,
For the SL2, it's just the T star P1.
oh,
And yeah, and basically like this smooth locus is just like the preimage of the smooth locus is everything but the central fiber, and I need that this symplectic form will extend over the P1, like over the zero section.
Dimension 2, it's just AD singularities.
Oh, so yeah,
Then there is a motion.
yes.
Flat line.
Yes, sorry. All right, and so then the theorem that like people actually have is that like in good situations, like you can study the algebra A like entirely in terms of the geometry of the resolution. And like basically like the more technical way of saying it is that this quantization of x naught induces like a quantization of x, and by that I just mean a quantization of the sheaf of functions on x instead of the ring. The definition is exactly the same, except for everywhere that I said ring before, you say sheaf of rings. And then there's and then if you have some module over this sheaf, like you can take its global sections and get something over your algebra where you have your h bar. And I'd almost like to say that that's an equivalence, but it's not quite right. It's an equivalence after you invert a power of h. H to the 1 over n, you have to invert, it turns out. But up to that, basically in good situations, like there'll be an equivalence between modules over this sheaf on the resolution, and then modules like over your original ring. And like it doesn't really matter what the form of this thing is, it just means that like now I can study things like upstairs. And like people call this like being like non-commutatively affine, because if you know of like an affine variety, that's like one that has the property that if you have like a quasi-coherent sheaf, and you take global sections, like you just get some module over the global sections, and that functors an equivalence exactly when your space is like affine. Okay. All right. So there's one other key property that this central quotient has that I want to figure out how to talk about in terms of geometry, and that's like the triangular decomposition. So like if you choose like a Borel, or like you choose, and like a pinning, then like you can split your G into like a positive part, a negative part, and then the carton. And so if you're doing SL2, the carton is the H, and then you're splitting it into E's and F's, being the positive and the negative stuff. And then there's like a really nice category of modules that you can study called the BGG category O, and that's the subcategory of all modules over my over my central quotient, such that the universal enveloping algebra of the positive part and the zero part, which in this case is the Borel, acts locally finitely.
what is that?
I was about to tell you. So that means that for all m inside of M, where this thing is a module over G lambda, then you need that the subspace spanned by acting with the Borel. This thing needs to be finite dimensional. Like as a vector space.
What does that say? I can't read.
So UB, so you take all the elements of UB, act on M, that's going to span subspace. And I need that to be finite dimensional.
Oh.
Like as a vector space. So like the key example of like something that you should have in mind is like a simple module. Well, they're finite dimensional. So if you act on anything, it's going to be finite dimensional. And then like something like a Verma module. So they're infinite in one direction. But if you act by raising operators, like you'll always get something that's like, that is finite dimensional. And so indeed, this category O is basically kind of like the smallest category that like contains the simple modules. That are compatible with the lambda that I chose. It's Artinian, so that means that like everything is built out of like a finite number of extensions of simple modules. And then it has enough projectives and injectives. And then the final thing is also that it's highest weight, so it has something that behaves like a Verma module. And so this is some like very nice category that people have been studying since the 70s. And like what I claim is that all the nice properties that this thing has are all because it comes from geometry.
Do you love these integer and integral?
I like it best when it's integral and regular, but you can study it at other levels too, but I'm going to just implicitly make that assumption. Okay, and so then in terms of like these symplectic resolutions, it turns out that this triangular decomposition just comes from a Hamiltonian C star action on your resolution that has an isolated fixed point set. So I'm not going to say exactly what Hamiltonian means. Basically, it just means plays nicely with the C star action, or sorry, with the symplectic form. The C star action plays nicely with the symplectic form in some way. In particular, it preserves it. And so if I have an action that's Hamiltonian and has isolated fixed points, then you can form what's called like the skeleton of X with respect to this action. And that's just basically the attracting set. So what you do is you look at like all of the x and x, you take the limit as z goes to 0 of z dot x, and you just ask like, does this exist or does this not exist? And for all the points where it exists, you put them in the skeleton. And it turns out that because this thing is Hamiltonian, this will actually give you a Lagrangian.
Maybe it's good to mention in this type CP1, it's 0 section and 5.
You're ahead of me, but yes.
No, if that's going to happen, okay, sorry.
Yes, yeah. So the example is that if you have like C star acting on P1 just by like rotating your circle with fixed points at the north and south pole, north and south pole, then like this thing induces a Hamiltonian action on the cotangent bundle, and this action, let's say that I've chosen the one where everything is flowing in to the north pole. Like that would be the one for just this, if this was 0 and that was infinity. And so one part of the attracting set will be this, but then when you're inside of T star P1, there'll actually be a bunch of stuff that flows into the south pole, and that'll be exactly the cotangent fiber to the south pole inside of P1. So this is like the example of like my attracting set. So can you guys see on this side? I'm worried I'm blocking you with the.
Blocking, yeah.
So basically it looks like that.
That's the south pole.
Yeah, this one's the south pole. That's the north pole. I had to flip it around.
You rotate it.
Yeah, had to rotate it. Yeah. Okay, so this is like the kind of thing that I have in mind for the skeleton. And then one can then like look at all of the modules over this deformation, this quantized ring that I have on my T star P1 or on my resolution. And you can ask which ones have support on the skeleton. And you can make a category that just like is all the ones that like live on the skeleton, and that category is what people call category O, like in a geometric sense. And like if you're a real expert, there's like a geometric condition, but I'm just throwing it out. And so there's a theorem, like due to these people, Braden, Licata, Proudfoot, and Webster, that says that like actually like this category O has like all the nice properties this category O for a random symplectic resolution has all the nice properties of the BGG category O that was associated to a Lie algebra, and in particular, the simple modules are just indexed by the fixed points, whereas like before they were indexed by like the Weyl group. And in this SL2 example, you can see that that matches. The Weyl group is two-dimensional, and there were two fixed points.
Generalization of Lie theory.
Yeah, so Kunkov calls these things like the Lie algebras of the 21st century. And so why I didn't put that into my talk, I don't know. It's like a good slogan, but.
You will give some example which is not to start.
I will give a little bit of an example, but like weirdly, like this isn't where I'm gonna stay. Like basically this is something I was doing in the past, and then there's gonna be a surprise. Okay, so the most surprising thing that they found was a phenomenon that they call symplectic duality. And so what they noticed was like this crazy phenomena, which was that like all these symplectic singularities came in pairs for some reason. They didn't give like a geometric, or sorry, they gave like a partial geometric characterization of the pairs, but they didn't give like something as good as like an SYZ fibration, like where like in ordinary mirror symmetry where people are like, these two guys are mirror if they're like, live over the same base as like dual torus vibrations. Like they didn't give something like as good as that. They just like said some things, like a couple of properties I'm about to tell you now, but like it was still very mysterious. So the first property is that the resolutions of one singularity should be in bijection with the C-star actions on the other singularity, like in an appropriate sense. Basically, like there's some chambers that govern both of these things.
Grading.
Yeah.
C-star action is like a grading.
Yeah, the C-star action is like a grading, and a grading on one space determines a resolution on the other space, which is like pretty weird. Yeah, and it's even weirder. So like if you just have an arbitrary grading, you get like a partial resolution. And like if the grading has like it has like finitely many fixed points, then that thing was a real resolution, not just a partial resolution. So it's like very, very weird. I mean, like there's like, this is like very mysterious. The other thing is that the set of, so now like suppose that on both sides I choose a resolution. Well, that means that also by this thing I have a C-star action on both sides as well. And then now let's say that I take fixed points for like the appropriate action. Well, there's gonna be finitely many on each side. Turns out, so one property is that they should have the same number of fixed points. So that's like pretty weird. And then like the craziest thing that they found was that actually like these two categories that I built satisfy a relationship called causal duality. And so like this is like really crazy. I'm not gonna explain this like super well, but like roughly the idea is the following. It's almost that they're equivalent. Like you would almost be right to say that like that causal duality means that these two categories are the same. But the form of the equivalence is actually supposed to swap the simple object with the projective object. And if you think about it, like you'll realize, like, and you do any computation, like you'll realize that there can be no equivalence of categories with this property. The reason being that if you have the endomorphisms of a projective object, everything is in degree 0. That's like the definition, like the x's are all in degree 0, that's what it is to be projective, no higher x's. But the simples have like tons of x's. So there can't be an equivalence of categories that does this because it's violating like the cohomological grading. So one way that you can fix this, the dumb way, my favorite way, is you just forget the cohomological grading down to a Z2 grading and then it'll be fixed. Like that, everything, it turns out on the simples would have been even, and then you'll just end up with everything in degree 0 on both sides. But the smart way of fixing it is that instead, like you can use Hodge theory in some crazy way to produce like a Z-graded lift of this category. And then you can find like an equivalence that basically, of the graded lifts, that basically swaps the grading shear with the grading shear plus a cohomological shift. So this thing is just like totally bizarre. Like it's like a completely like bizarre thing that they found. And like everybody was just like really confused like about like what this thing is. So let me just give you a bunch of examples of these like pairs. And then I'll tell you like what the resolution was. No pun intended. So the first one is like the nilpotent cone for the Lie algebra G is dual to the Langlands dual nilpotent cones. That's the, so that's like an old theorem of Beilinson, Ginsburg, and Sorgel. about like the classic BGG category O. And you shouldn't know all of these examples. Basically, I'm hoping that like people will know like each person will know one of these examples. It's kind of like more what I have in mind. So then the second example like comes from Lie theory, and it's a generalization of the first. And now that says like suppose that you take like the closure of a nilpotent orbit. Let's just say that I'm in type A. So then a nilpotent orbit is in bijection with a partition, like just given by like the Jordan blocks of your nilpotent matrix. And there's an operation which will take you to another nilpotent orbit, which is just transpose the partition. So now I've got like another orbit. They call it the Spaltenstein dual. And in general, it would live in the Langlands dual orbit. Like for the one I just gave, it's self-dual, so nothing happened. And then what one can do is you can take what's called the slice to the orbit. So that's basically, it's like some subset that starts in my orbit and then touches all of the other orbits like exactly one time. And it turns out that like these two things are both symplectic singularities. They admit symplectic resolutions in most scenarios, and the category O's are like dual.
What? The last sentence?
Oh, the category O's are causal dual, like the last weird property. So this is like kind of insane. And the very simplest example of like this sort of a phenomenon is if you take like the second smallest nilpotent orbit, the smallest one's 0. So that one will be resolved by T star Pn often, like if you're in type A. And then like one can take the Spaltenstein dual. Turns out you'll get the second largest orbit. And if you take the slice to it, you'll get some two-dimensional singularity. And it turns out that it'll be and if you resolve it, turns out you'll get the resolution of the Kleinian singularity for the cyclic group Zn plus 1. So let me actually draw a tiny bit more about this one. So there's some very pretty pictures you can draw for this example, which are kind of like toric pictures, where let's say that I draw T star P2. And then if I choose my C star action, it turns out you can represent it as some sort of an arrow. So let me tell you what this is a picture of, and let me shake this because it's going to go to sleep. So this is a picture of a particular Lagrangian inside of T star P2. So these are called toric pictures, if you know about toric varieties. So this is a picture of a P2 glued to, this interval here is a P1. And this space here is the conormal to the P1 inside of P2. And then say that this is some particular point inside of your P2, this little dot here. This thing here will be the cotangent fiber to that point, to this P2. And these are the only chambers for this particular direction where if I think of this direction as giving me a linear function via the dot product, these are the only ones that would be bounded for that. And so what this is telling me is that my attracting set for some particular C star action on this P2, the one that I mean is let's say that this thing is given by this, is given by the vector 1, 2. I mean, it acts by weight 1 on the first fiber and weight 2 on the second fiber. So you can look at the attracting set for this thing. It'll be the union of these three varieties. And then the mirror, I said, would be the resolution of C2 mod Z3. And this one has a similar toric picture that looks like this. And here, your C star action, I'm going to draw using an arrow in this direction. Here you also have three chambers that are bounded. And what you can find is exactly what I said. These things have the exact same number of fixed points, namely these three and these three. And then this duality actually ends up swapping these unbounded chambers, of which there's two, with the bounded chambers over here. And this unbounded chamber goes to, this bounded chamber goes to that unbounded chamber. So it's some very weird looking matching of the fixed points, basically the way that these things go. But this is one that you can actually sort of draw in a very concrete way.
The bounded/unbounded chambers, that's there's a rejection between them and project vector simple modules?
So there's a simple module for each chamber, and there's a projective module for each chamber. So there's three simples, and each one has a projective cover. So that's
part of the duality.
That's part of the duality, yeah. Oh, well, so the duality says that, yeah, so there's, for each of these guys, there's a simple corresponding to each of these chambers, and there's a projective corresponding to each of these chambers on this side, and the simple here goes to the projective corresponding to the dual fixed point, and vice versa.
So this duality does not preserve dimension?
Does not preserve dimension, so it's not like a mirror symmetry. So that's like pretty weird.
So it's not like 2D mirror symmetry.
No, it's not a 2D mirror symmetry. That's right. I called my talk 3D mirror symmetry, so I've given it away. And then there's a couple of other examples which like maybe you've had enough time to read. It's not so, they're not going to come up again, so I'm running low on time, so I won't read them. But yeah, so people were like really confused. They were like, wow, like there's like this like crazy duality. It's like, it's really weird. It's not mirror symmetry. It's like relating varieties of like a totally different size. It has this really weird, like very strong categorical consequence. Like what on earth is this? And like you know, one day, separately, like both Ben and Nick, Webster and Proudfoot, were giving talks, and like in separate talks, Gukov and Witten were like, I know exactly what you're talking about. Like we've seen this before. They were like, I've seen every pair of examples that you have. They're all Higgs and Coulomb branches of the moduli space of vacua in a 3D n equals 4 QFT. Silly. Don't you know? And so anyway, so like basically like they like looked at this, and you know, they like went and looked at some papers, and it turns out that like the Coulomb branch at the time like really didn't have like a very good mathematical definition. So like you actually like couldn't do anything with this, and like people, and like, you know, there was no categories like in this 3D QFT world. Like it was just people computing like partition functions and various sorts of simple things. So this was like, you know, kind of interesting, but like also kind of useless. And the other thing that they said is that like, there's like a duality of these 3D n equals 4 theories called 3D mirror symmetry, and like it exchanges the Higgs and Coulomb branches of like mirror theories. So that's probably what symplectic duality is. But like that was like all they gave us. Like, you know, like I have the email, and that's, and that was it. But like that does like pose the question, like, so there is this physical thing called like 3D mirror symmetry, and like can like one actually get symplectic duality out of this thing, like in the same way that like you know, people got like 2D mirror symmetry out of 2D mirror symmetry. And so like in one of my very first papers, where I teamed up with where I got recruited by a bunch of physicists, I should say. I didn't find them, they found me. We showed that the answer is yes. And actually though, that like the symplectic duality thing was really just like a shadow of like something like entirely different. And this is like some crazy like artwork that I commissioned from a grad student at Berkeley named Elliot Kinzel, like to try and like.
You talks and these are his notes.
Yeah, basically. Like, well, yeah. I mean, like I like talked to him for a long time and was trying to get him to just. He's the artist. I was just like, just represent like what I've been talking about, like in some like sort of way. And so like what he like represented is that like over here there's this gigantic tree, which he calls the mirror symmetry, which like puts together like mirror symmetry and like all these different dimensions. And then like it has like some pale shadow from like from the sun coming down, projecting onto the ground. And over here, like this is like where this symplectic duality was living. I don't know. I mean, I like this picture very much. I don't know whether it's possible to learn anything by staring at it for long enough, but I really enjoy it. But yeah, so let me try and tell you just like a little bit of like what we found, and then maybe there's a lot here, and I'm happy to talk about this picture for hours. All right, so let me just say like what on earth, like when people say 3D n equals 4, what on earth do they mean? That's like the first question. And I'm just gonna use always like this exceptional isomorphism between spin 3 SU2 and SP1, SP1 being the unit quaternions, going to use this like all the time and without comment and probably by accident. So I want to just call that out. And under this isomorphism, the spin representation corresponds to the representation C2 of SU2. Okay, and then so then what is this 3D n equals 4 algebra? So there's the ordinary just 3D Poincare Lie algebra, and I'm in Euclidean signature here. And that's just the translations, like together with just their action of the spin group, and that's like a semi-direct product. That's like a very like old thing. And then when people say something like 3D n equals 4, what they're naming for you is a super Poincare Lie algebra. So that's like an extension of this Lie algebra by an odd vector space. And here, and the n here, or sorry, and so it's got one copy of the spin representation if there's only one in your dimension. So that's this C2E. So I've labeled it by E because it's supposed to be acted on by this E, which as the spin group would be, it'd be acted, sorry, as the spin representation should be, it should be acted on by the Euclidean group. And then you should take some number of copies of it, and that's the n. So here I'm going to take 4 copies of it, and in order to make this thing into a Lie algebra, this thing needs to have a symmetric pairing, or like a metric. And then you can use that to write down a symmetric pairing from here to the translations. But like it turns out that for everything that I want to do, it's not just good for me to choose any 4-dimensional vector space with a pairing. It's better if I take the following. I should take 2 copies of C2 and tensor them together, and then like that lets me represent the exceptional isomorphism between spin 4 and SU2 times SU2. So like that's like what's going on here is like, so, and there's this extra like group that's acting on everything called the R symmetry, which is the automorphisms of this Lie algebra that just fix this bosonic part. And that like, and they just act on this vector space here, preserving this symplectic form. So let me just say one thing about like what this thing does. So roughly the way that like the pairing works on this is that C3, which is your complexified translations, this thing is just the symmetric square of your spinner. So this thing is acted on by the Euclidean group, and maybe I should have put an E on that C3. And so there's a nice thing like this, and roughly like if I have some big tensor here where I have some element of my Cn comma G and some element of my spin group, and I want to like take their product, well I should take the inner product of the parts that are labeled by this 4-dimensional vector space. That'll give me some number, and then I should multiply it by the symmetric square of this thing. So this whole thing, whenever you bracket things, it always lands in the translations. That's the only important thing you need to know. Like whenever I bracket these odd things, they always land in the translations. Okay. And I could write a presentation for this, but it wouldn't be very happy. And then like one can ask like, what on earth is this thing for? And so like physicists like represent like everything in the field theory in terms of the representations of this superalgebra. So like everything they write down, like we'll have like C indices and E indices and H indices depending on which thing is acting. And like in order to understand anything, like you have to just like understand that Lie algebra really well. But as a mathematician, the thing that this thing is for is that it lets you get TQFTs out of supersymmetric quantum field theories. So I don't really like know what a supersymmetric quantum field theory is, but I know what a TQFT is. And the way that you get them is you look for these things called supercharges. So that's like you look inside of like the odd part, the odd part of this algebra, this part here that's labeled by the pi. And you look for one such that it brackets with itself to give you 0. And like roughly like what that tells you, and the bracket of something odd with itself is just really q squared, or 2 times q squared. And so like what this thing is telling you is that anything that's a supercharge is something that you could use as a differential, like in cohomology. Like it satisfies q squared. So maybe like if you just add it onto the Hilbert space as a differential, things will get simpler. And indeed, like that's true, and then that's what they do. The amazing thing is that if your q is topological, so what that means is that when you bracket with q, it surjects onto the translations. The field theory that you get will be a topological field theory by turning on this q. And the reason that that's true is because if all the translations are in the image of Q, that's telling you they're Q exact. They're all Q of something. So in Q cohomology, they're all going to be closed. So that or say they're all going to be 0. So that tells you that taking translations will do nothing to your theory, which means it's topological. Like when you move in space, like nothing changes. So this is was Witten's big insight. And he first discovered this thing when he was, maybe first he did it with Donaldson theory, and then a second thing he looked at was he was trying to describe homological mirror symmetry, coming from some other supersymmetric field theories. In this case, 2D n equals 2 comma 2 is the amount that you have. And this algebra, it turns out, has 2 different supercharges in it, the A type 1 and the B type 1. They both square to 0. And you can take the cohomology to get to these 2 different field theories that they call the 2DA and the B model. And there's this 2D mirror symmetry, which is acting on this Lie algebra. It's actually just really boring. It's just an involution of the Lie algebra. That's all 2D mirror symmetry, all mirror symmetry is. It's just, I have a Lie algebra and I have an outer automorphism. And it swaps these 2 supercharges. And from that, you can deduce that it must swap the A model and the B model. That's sort of how they figure these sorts of things out. And then they realize that the 2D TQFTs you get, you can model them just by some categories. So let me say what this means in a little bit more detail. So this 2D n equals 2 comma 2 Kähler sigma model. So all that means is you're studying some Kähler manifold X, and I'm just looking at maps from a 2 manifold into it. That's all sigma model means. So let's call my map phi. So basically, in the supersymmetric field theory, I have this map as one of my fields, and then I have a bunch of fermions and some other things that I don't want to talk about. And they satisfy some really horrible PDEs. And I don't want to study those PDEs. But a thing that one can do is it turns out that the space of all of these fields, it's just some super manifold. And you can just take and it has an action of this Lie algebra. And if you can just take the fixed points under this supercharge, and you'll get some submanifold. And the submanifold that you'll get if you do the A-type supercharge is just exactly the space of maps where they satisfy the holomorphic map equation, just del bar of phi is 0. And if you do it with the B-type supercharge, you'll get a similar thing where actually your map will just have to be constant or locally constant. You'll just get d of it is 0. And that's why people tend to forget that there's actually a curve in the B model. In the A model, you're studying holomorphic maps from Riemann surfaces. People remember Gromov-Witten invariants. But in the B model, they're where's the curve? And it's because it's constant maps, so people just throw it out, usually. But it has some derived structure that you should remember, but I won't talk about that. But anyway, and then the corresponding categories that you get are either just the Fukaya category or the category of coherent sheaves by studying these 2 equations. And I'll say that whether you get something that looks like de Rham cohomology or Dolbeau cohomology in your morphism spaces, that's basically determined by the fermions. If you were very careful and actually tracked all the fermions, which I didn't do for you, and worked out how they behave, you would actually could derive the things about de Rham cohomology being the morphism spaces and coherent sheaves being the morphism spaces over here. Okay, and the reason I bring this up is because I want to do the same thing in 3D. So it turns out that this 3D algebra also has some A-type supercharges and B-type supercharges, and they're compatible with the ones in 2D in the following way. There's an embedding of the 2D supersymmetry algebra into the 3D one, and I have my supercharges in 2D, and I can just take their image in 3D, and it turns out that they're still topological supercharges. And so then one can just go ahead and take the twists with respect to these things. You'll get something I call the 3D A model, something I call the 3D B model, by taking either the cohomology for QA or for QB, and they're exchanged by mirror symmetry again. Basically, there's an involution on this 3D algebra, which is compatible with the one in the 2D, or equivariant, makes this map equivariant if you consider the one for the 2D supersymmetry algebra, and you can just start playing the same game.
Is there an analog of the Fukaya discussion of maps of 2D things into some target in 3D?
Yeah. Yes. Yes. So that's what we're going to talk about. And so then one can study, So in this symplectic duality game that I was talking about, people were studying these holomorphic symplectic varieties.
Wait, 3D, that's 3D complex. Hyperkahler.
No, so M is a 3-manifold, like an ordinary 3-manifold, and X is a hyperkahler manifold.
Oh,
and
mapping into it.
yeah, it's mapping into my hyperkahler manifold. So T star P1 is like your canonical example of what X is, although maybe not, because I'm going to make it an assumption that's going to rule that out, but that's good enough. So it turns out that I said that Gukov and Witten told us that all these symplectic singularities were all Higgs and Coulomb branches. So in particular, he says that even though we weren't using it, we should have known that they were hyperkahler actually, not just holomorphic symplectic. So in particular, they have like a metric, like a nice metric. And so then they're the kind of thing that could be the target for this hyperkahler sigma model. And it works in exactly the same way. And then I need to remember just one extra piece of structure, which is that in these 3D theories, there was some group that I had called SU2H in the R symmetry. I'm going to identify it with SP1, and it acts on X by rotating the complex structures. And that'll be important in a second. And anyway, so in the supersymmetric field theory, you have these maps and these fermions. It's very complicated, but one can do the twists and get something simple. The equation that you get is just the exact same equation on the 3DB model. It's just that your map needs to be locally constant again. It doesn't use the hyperkahler structure in any way. Although I do want to point out that when I chose this 2D embedding, I determined a complex structure on X, and the B model will depend on that. So it's going to be something of algebraic flavor in X, and you can sort of tell it's not going to have any enumerative geometry counting problems because there's just kind of constant maps.
What structure on the 3-manifold do you need to be able to invariantly write down that pink equation?
So on this side, I don't need anything, but on this side, I'm going to need a spin structure.
You don't need anything to be able to make sense of the left-hand side?
I do on the left-hand side. On the right-hand side, I don't need anything.
No, on the left-hand
On the right-hand side, I'm going to need a spin structure.
No, but I'm asking about what structure do you need on the left-hand side to make sense? Because in the 2D case, you need a holomorphic Riemann surface. You need a complex structure. So what do you need on the 3-manifold that's analogous to the complex structure to 2D?
I think I just need the metric.
Metric. Okay.
I just need the metric on the 3-manifold, and I need the and I need a spin structure. I think is all I need.
In Gromov-Witten theory, you have a moduli space of domains.
Yeah.
So here you have some sort of moduli space.
So that's So normally, so I would say that maybe we haven't gotten that far. But the other thing that I would say is that in Gromov-Witten theory, you normally couple to gravity. And when you couple to gravity, then you're really interested in varying the metric. And that's what gives you all these integrals over this moduli space. And I'm not going to couple this thing to gravity. So for me, it's just a fixed,
okay.
A fixed M3. I'm not going to look at it in a, I'm not going to look at it in a family. Yeah, that's a good question. Anyway, and so the equation that you get is roughly that it turns out that this twist, if you are very careful, it identifies the spin 3 Euclidean with this SP1 that's acting on X. So it turns the tangent space of this X into spinners. And then so I need some spin bundle, and I can use that to basically get a bundle of X's over M3, which is twisted by the spin, just using the associated bundle connection. And then the equation you have is just a nonlinear Dirac equation, which if you trivialize your M, if you just make it R3, then you can basically write it in this form. And you see it's kind of a generalization of the holomorphic curve equation. In particular, if I were to set X to be 0, or ask it to be constant in the X direction, then this term would drop out, and then I could just pull out a J, and I think I would get either the anti-holomorphic curve equation or the holomorphic curve equation, depending on my sign, say.
So the left side with the Fourier equations.
So this thing is the same as the Fourier equation. Well, sorry, twisted by a spin, but yeah.
And on the right side, the complex structure you use is the equator for the C star rotating the sphere, right?
I mean, it depends on what I chose. For this C star, yeah, it's the, no, it should be the poles.
Well, like it's affine or quasi-projective?
Quasi-projective.
So that's poles.
Yeah. Yeah, that's right. Okay. And I should say that for all the things I really want to do, I actually need to look at gauge theories where you also have some group in the game, and this thing becomes the Seiberg-Witten equation, but I'm not going to have time to talk about that. But this is interesting enough, and people don't know how to do it. So figuring out how to build the two categories here is pretty interesting. So, okay, so people expect that these 3D TQFTs are actually determined by a two category. And the picture that physicists would usually draw is usually Poincare dual to the picture that like a mathematician would draw. So the picture that like a physicist would have in mind is they would say like, oh, you should look at like R plus times R2. And then you should look at the boundary, and then the objects of your category are going to be boundary conditions. So that's like what's labeling like this region of the boundary here, these A, B, and C. And then the morphisms between two boundary conditions should be like a boundary line separating like the two boundary conditions. And then like the two morphisms should be like a boundary defect or a boundary local operator separating two lines. So like physicists would draw pictures like this, and when you set up like your counting problems in the A model, you would set up things like this. But then a mathematician would take the Poincare dual of this and say like, this region is becoming this dot, which is an object in my two category. That dot is an object in my two category. That dot is an object in my two category. These like lines are becoming vertical lines. The horizontal lines are becoming vertical lines, and then basically the dots are becoming two cells. So you just take Poincare dual of the picture.
So when you say 3D TQFT, you mean extended TQFT?
Yeah, extended. Although, I mean, it should have everything, but I'm mostly focused on the extended part, what's associated to a point. So like, okay, so we should be able to build one of these things either out of this this Futter equation or out of this 3D B model equation. And okay, let's see how much time I've got. Ooh, okay, so maybe I should.
Do you know that you end up with a TQFT after you twist a 3D sigma model?
Give me a minute. I've only got 4 minutes, so I've got to like think about what to do. And I can make it. I just need to think. Okay, so yeah. So what one wants to do is like understand like these two categories, and I'm going to give you like a very heuristic sketch on like how one like actually like does that. So the way you do it. The way the physicists would say to do it is like you should take your 3D theory, look at it on like R2, say times like an interval. Suppose I want to like understand like the Hom spaces. I should put a boundary condition on each side of the interval. So that's just going to be something about some maps into my hyperkahler manifold. And when I split this space up, I'm going to get a complex structure on this, which I'm going to assume is Louisville, or is has a Louisville structure. And then they would say like, okay, well just rewrite your maps from your 3 manifold into this target as maps from a 2 manifold into some fixed target space. And it turns out that like this is just using like the tensor, like the product Hom adjunction, right? Like maps from a product like is maps into maps. And then it turns out that in order to write down the 3D PDEs in terms of the 2D PDEs, you'll need to pick up some superpotential that like is going to take care of like the cross derivatives. And in this case, it's like the holomorphic symplectic action functional. So you just pull back your Louisville form along your, so for each gamma, which is a map from an interval into your map, you pull back this Louisville form and integrate it. And like that's just exactly like what shows up in the Fukaya category, except for everything's complex now. And then if you want to like, be able to make this thing to, get the 3D PDEs out of these 2 PDEs, turns out that like you will actually need to constrain like what happens on the boundary of this interval. And like it's a pretty easy computation to show that actually, very easy computation, to show that like actually they need to lie on like exact holomorphic Lagrangians. And so the thing you learn out of this is that and this is the same way you learn like in the Fukaya category that your objects are Lagrangians. Here you learn that they're like exact holomorphic Lagrangians. So that's what the objects of these two categories should be, it turns out, in either case. And then one can try and like compute the Homs. So one alters this mapping space I had in these potentials, like in order to constrain the endpoints to lie on my Lagrangians. And if you want to know what the maps between the two are, you just look at the Fukaya-Seidel category of like these two path spaces. In the same way, or the matrix factorization of this path space, depending on whether you want the Homs in the A twist or the B twist. And this is kind of, yeah. Yes, let me write that thing up again so we can see it all at the same time. Same objects. That's different than the Fukaya category. Yeah, so it's the same kind of objects. They're both holomorphic Lagrangians, and then this space is just this X space. It's just the space of maps into my target, except for I'm going to constrain the endpoints. And then the superpotential is just the exact same superpotential that I wrote down before. It's just that, so I'm going to pull back my Louisville form and integrate. But now you just have to add some boundary terms to fix that depend on the Lagrangian to fix that. So a very special case is when you have like a cotangent bundle. And then these things are like the graph of, are like the graphs of like holomorphic functions on X.
What's X?
Something random, anything Kahler. So I guess you've been using X for hyperkahler, so let me call it Y just to be different. So I have some random Kahler manifold. If it's cotangent bundle, you can look at like the graphs of holomorphic functions from Y to C, and then you can ask like what are the Homs between these two guys. And it's a theorem on the first side due to Kapustin-Rozansky and Saulina, that on the B side, this thing just turns into the category of matrix factorizations on Y with the superpotential F0 minus F1. And on the A side, it becomes the Fukaya-Seidel category of the same exact thing. And this is a theorem of Doen and Reshikov, very recent. Okay, and the last, so I actually can finish. So the one crazy thing about these is that both of these categories have the same periodic cyclic homology, which ends up being actually just the vanishing cycles, the cohomology of the vanishing cycle sheaf with respect to this big function. Both matrix factorizations and Fukaya-Seidel have the same HP. And so what this like sort of tells us, and this was a conjecture that we made a long time ago, is that you have these, given a 3D n equals 4 theory, you have these two categories, and if you apply HP to the Hom spaces, the thing we expect to have happen is you'll find category O for a particular symplectic manifold, which was this Higgs branch of the theory, which I didn't get to say what it was. And like even more so, what you expect is that if you have two mirror theories, there'll be some equivalence of the A model on one and the B model on the other, and vice versa, and that'll categorify the symplectic duality equivalence that we said. And the final thing is that like I've made some progress in proving this using some algebraic model for the 3D A model. I can't do the PDEs that are required to do it for real. I'm too weak, but I've been trying to find like some symplectic geometers, mostly Simone, to try and like actually like show that what we did can be done using analysis. And so I'll stop.